So if you're into AI, you know the feeling, right? A new model drops, another paper gets published, and bam, it feels like everything you just learned is already out of date. It's just this constant sprint to stay on top of things. But what if there was a better way to look at it all? A way to understand the entire field without having to start over from scratch every few months? Okay, let's get into it.
I mean, the speed of AI development is it's wild. It can make everything feel so chaotic. One day, everyone's talking about transformers, these amazing models for language. The very next, it's all about state space models, this totally new architecture that's supposed to be even better. Trying to master every single new model is, well, it's exhausting. But maybe we're all focusing on the wrong thing. What if the secret isn't in the specific models, but in the timeless process that actually creates them?
Okay, so this slide breaks it down perfectly. On the left, you've got the model-based view. That's what most of us are used to. We chase the shiny new architectures, but it's a moving target. It's always changing. But on the right, we have the process-based view. This focuses on how a model learns, which is a framework that has been incredibly stable for years. And that is our map. It helps us navigate this crazy, fast-changing world of AI by showing us the roads that are always there, no matter what new tech gets built on top of them.
All right, so if we're going to use this map, we need to know the key landmarks, right? Well, the whole process can be broken down into 6 core components. And these apply to pretty much any deep learning system you can think of. You know, the stuff that powers everything from your phone's camera to your music recommendations. Let's explore the 6 building blocks that make it all happen. And here they are. These 6 modules make up the entire pipeline, from getting the raw data ready all the way to helping the model evolve over time. You can think of it like a universal assembly line for intelligence. Each station has a super specific job, and they all have to work together perfectly to create that final product, a smart, capable AI model. So let's break down what happens at each of these stations. Okay, first up, input pre-processing. This is everything that happens before the model even sees the data. You can't just throw a messy folder of pictures or a raw text file at an AI and expect it to work. Nope. You have to clean it, format it, maybe even create new examples from the old ones. It's kind of like a chef, you know, carefully prepping all the ingredients before they even think about lighting the stove. And this step is, well, it's everything. Because if you start with junk data, you're going to get a junk model. It's that simple. All right, next up is the model architecture. Now, this is the part that gets all the headlines. The latest transformer, the newest diffusion model, it's the blueprint of the model itself. But in our new framework, it's just one piece of a much bigger puzzle. It defines the shape of the machine that's going to do the learning, but it doesn't define the learning itself. Think of it like choosing the kind of car you want to build, a fast sports car or a powerful truck. The architecture you pick determines what the car could do, but it doesn't actually teach it how to drive. Okay, so how does the model even know what it's supposed to do? That's where objectives and regularization come in. The objective is the goal. Simple as that, like correctly identify the cat in this picture. And regularization adds the rules, telling the model, hey, don't just memorize the training examples. It's basically the rule book for the learning game. So for our cat model, the objective is to get as many cats right as possible. But we add a rule, a regularization technique that says, don't just memorize the pixels of these specific cats. You need to learn the general idea of catness.
Now this is where we get to the real magic, how the model actually learns. The learning dynamics are the algorithms that physically change the model's internal wiring. When the model gets something wrong, this module figures out exactly how to tweak its massive network to do better next time. It's the engine of improvement. A really common algorithm here is called gradient descent. Picture a hiker trying to find the lowest point in a valley, but it's super foggy. They can't see the bottom, but they can feel which way is downhill right where they're standing. So they take a tiny step in that direction, check again, and take another step. That is exactly what the model is doing, millions of times, always moving in the direction that makes it a little less wrong.
So a model can get a perfect score on its training data, right? Ace the test. But what happens when you give it something it's never seen before? That's the job of evaluation. This is the quality control department. It pulls the model off the assembly line and tests it on totally fresh data to see how well it's actually learned to generalize. This is where we catch huge problems like overfitting, which is basically when a model just memorized the answers to the test instead of learning the concepts. An overfit model is pretty much useless in the real world, and this evaluation process is designed to sniff it out. And that brings us to our final block, adaptation and evolution. See, a trained model isn't the end of the line.
This part covers how we can take a big, general model and adapt it for new, specific jobs, a process we call fine-tuning. This is how models grow and stay relevant. For example, you can take a giant language model that's been trained on the whole internet and then fine-tune it on a specialized dataset of medical records. You're not teaching it English from square one. No way. You're taking all that general knowledge and just specializing it. You're turning it into an expert.
Okay, so we've got our 6 building blocks. Now let's see how they actually work together. The most important interaction is what's called the inner training loop. This is the engine room of AI. It's where the real moment-to-moment learning happens, furiously cycling through those first 4 modules: input preprocessing, architecture, objectives, and learning dynamics at an unbelievable speed.
Here's how that high-speed cycle works. First, you prep a little batch of data and you feed it into the model. Then, the model does what's called a forward pass. It makes its best guess based on what it knows so far. Next, the objective calculates the loss, which is just a fancy word for error. It figures out exactly how wrong that guess was. And finally, the learning dynamics use that error signal to make tiny little adjustments to the model, nudging it just a little bit closer to the right answer. And then, the whole thing repeats, billions of times.
That inner loop is going 1,000,000 miles an hour, but you can't just let it run wild. To manage this whole process, we need 2 outer loops that work on a much slower schedule. Think of them like the conductor of an orchestra. They make sure all the individual players in that fast inner loop are working together to produce a beautiful result.
So the first of these outer loops is the evaluation loop. This is like a scheduled checkup. After a certain number of those frantic training cycles, the whole process pauses and we kick off an evaluation. During this checkup, we test the model on that unseen data we talked about, using all sorts of metrics to get a really clear picture of how it's doing.
And that checkup all boils down to one critical question that decides what happens next. The results of that evaluation create a fork in the road for the entire training process. Do we keep going? Do we make some changes? Or do we stop? The answer all depends on whether the model is still getting better or if it's good enough.
So what are the 2 options here? Well, if the model is still improving, a signal goes back to the inner loop to keep training, maybe with a few tweaks. But if the model has hit a plateau, meaning it's not getting any better, or if it's already hit our performance target, we stop the loop. We save that version of the model, and that snapshot becomes our pre-trained model ready for the next big thing.
But what happens after you've got that shiny new pre-trained model? Well, that brings us to the outermost loop, adaptation. This kicks in when we take our model and realize, it's not quite good enough for this new specific task. This loop is all about that fine-tuning process, connecting the model's huge base of knowledge to new challenges. It's just like that world-class chef we talked about. They already have a powerful foundation, so they're going to learn a new cuisine way faster than someone just starting out. So when you put all of this together, the 6 modules, the 3 nested loops, you get this complete and most importantly, stable picture of how AI systems actually learn and get better. It's a really powerful way to think that helps you cut through all the noise and hype. It's like having the blueprint for a house. Suddenly you can see how all the different parts, the foundation, the plumbing, the wiring, all fit together to make the whole thing work.
The source material we're using calls this a process-level scaffold. And honestly, that's the perfect way to describe it. The specific models and algorithms that you plug into these different modules, yeah, they're going to change, for sure. But the scaffold itself, the fundamental process, that remains. It's like the chassis of a car. You can swap out the engine, change the tires, totally redesign the body, but that underlying frame that holds it all together stays the same.
So now, instead of feeling totally overwhelmed by the next big model announcement, you can actually ask the right questions. Okay, which of the 6 modules does this new thing improve? How does it change the dynamics of the 3 loops? You have the blueprint now. You have the map to navigate the incredible, fast-moving future of AI. The only question left is, with this new way of seeing things, what will you build?